I would just say, for some purposes, I think it's a great package. Of course, it's not, it will not be the right thing for everyone, but we think it's useful. And so try it out. And so with that, let me now move on to a second package, and this work would now be shared with you by Huanchen. So, so Huanchen, if you unmute yourself.
Yeah, okay. So hello everyone. In my part of the talk, I would like to share some of our recent progress on code developing for quantum chemistry DMRG. Next slide. First, I would like to explain why the DMRG code currently available on the market does not meet our goal, and then what can be the advantage of a new code. On one hand, there are many good and well-known tensor-based DMRG libraries, such as iTensor, which is developed mainly for solving physics problems. They can support a variety of systems, including spins, bosons, and fermions, but most of them are not efficient enough for large-scale quantum chemistry problems. On the other hand, there are also many code developed for quantum chemistry DMRG, such as PyBlock developed by our group and Quimb and PSU. This code can be easy to use as a binary, but modern tensor network language is not fully reflected in both PyBlock and Quimb and PSU, which can make it difficult to do development on the two code. To the best of our knowledge, there's no quantum chemistry DMRG code that can achieve efficiency similar to PyBlock and be easy for development at the same time. So our goal is to develop an efficient and easy quantum chemistry DMRG code based on modern matrix product state and matrix product operator language. Next slide. To achieve the best efficiency, the code should support an efficient representation of block sparse tensors, and each block in the tensor should be labeled by conserved quantum numbers, which is important for efficiency and also for being able to targeting a specific symmetry sector of the system. So with a highly optimized sparse tensor library with quantum numbers, we can build MPS and MPO in pure Python language. They are just a chain of these sparse tensors. The MPO and MPS implemented in PyBlock 3 can support most common linear algebra operations, where the MPO can be viewed as a matrix and MPS can be viewed as a vector. For example, the addition, dot product, norm, and SVD operation can be expressed in a way that is very similar to that for manipulating non-parallel arrays. This will make it very easy for translating tensor network graphs to the code. Finally, we have implemented a variety of sweep algorithms, including ground state DMRG with perturbative noise, finite temperature DMRG using time step targeting method, time-dependent DMRG, and dynamical DMRG, which can be used, for example, for solving one particle Green's function. All of these can be implemented in PyBlock 3 using less than 100 lines of the code. Next slide. Here, I would like to show two examples for the usage of PyBlock 3. The first example is the exponential of an MPO acting on an MPS with ancilla size, which is one step in imaginary time evolution for finite temperature DMRG. Here, the RK4 approximation is used. The code for MPO acting on MPS basically uses the same grammar as that for NumPy array matrix vector multiplication. The second example is a minimal implementation for ground state DMRG. In this figure, the sandwich structure formed by bra MPS, MPO, and cat MPS is a core data structure in DMRG. There will be multiple sweeps. In each sweep, there will be a loop over size, and at each iteration, two tensors in the MPS will be optimized by solving the eigenvalue problem for the effective Hamiltonian formed by contracting and canonicalizing the sandwich structure around the two effective sides. In PyBlock 3, the effective MPS and Hamiltonian can be conveniently constructed and updated using the slicing notation in Python. For optimal efficiency and accuracy, the code for practical applications will be longer than these minimal examples, but the skeleton will be the same. Next slide. Finally, we compare the performance of the PyBlock 3 and a highly optimized conventional quantum chemistry DMRG code called Block 2, tested on chromium dimer molecule. This system is unachievable for most for most purely Python-based DMRG code, since both the MPS and MPO bound dimension are near 1000, we can see that compared to the C++ code, PyBlock 3 gives roughly the same converged energy, and it is only a factor of 2 slower than the C++ code, which should be acceptable. PyBlock 3 is now freely available on GitHub, and I hope it can be useful for some of your research projects. That's all for my part of the talk.
Okay, so so finally we'll switch to the Quimb circuit and tensor network library Quimb, which is developed by Johnnie. Johnnie, can you unmute yourself?
Yeah.
Okay, all right.
Hi, yeah, so Quimb is another Python library for kind of general quantum many-body calculations, but is really focused now on very general tensor network algorithms. And part of that general focus means it's got a very capable quantum circuit simulator. And so the idea is kind of to generally approach all types of quantum tensor network systems, or not just quantum, but all tensor network systems. So beyond kind of DMRG algorithms to higher dimensions, very unusual geometries, like some of the tensor networks I'm showing here. And next slide. So the motivation for doing that is that whilst it you can write kind of DMRG code fairly easily in 1D, although it's hard to make it fast, it can be quite fiddly to code up these tensor network algorithms in higher dimensions and very complex geometries. And particularly if you write some kind of nice algorithm, it can be quite hard to transfer it from one geometry to another geometry. So Quimb tries to do a couple of things to make it easier to do this kind of general tensor network algorithm development. The first is to decouple as much as possible these methods from the geometry. So lots of the methods work by taking the local graph structure into account, or the full graph structure into account, rather than explicitly expecting some kind of geometry. And so this really is like an actual tensor network representation at the core of Quimb, which you can manipulate and plot, and 1D and 2D algorithms are just subclasses of this. Another thing is Quimb tries to decouple as much as possible the actual underlying array implementation from the algorithms. So these algorithms are very linear algebra heavy, which is great for Python. And you also only need really a few functions to be supplied. So Quimb tries to abstract out all of these array methods using this library autoarray, and that means that you can write code once and hopefully it generalizes from your CPU to GPU or MPI tensors, or you can trace through the whole computation. And importantly, it means you can use a whole host of different autodiff libraries for computing gradients of tensor computations. Next slide. So just to give a very high level overview of some of the things that Quimb can do, it does have easy kind of reference versions of these many-body algorithms like DMRG, and also now 2D algorithms for kind of simple quantum many-body lattice models. And then it also has quantum circuit simulation. So because it can represent any tensor network geometry and handle these, that makes it very naturally suited to quantum circuits, where you get these very odd kind of irregular geometry tensor networks naturally. And for these, you can really get state-of-the-art performance in Quimb, especially for medium to large circuits. And then one of the important things, like I mentioned, is this autodiff optimization. So this applies to both of these things, in fact. You can construct algorithms that work on many-body ansatses, or on, for example, the wave function or the local energy terms of a quantum circuit simulation. And because we can pass off all of the array operations to some library like PyTorch, you can perform global tensor network optimization on these, which enables a huge variety of very diverse things to compute. Next slide. So just to give a very, very brief flavor of that kind of thing, particularly related to quantum circuit examples. So you can compute just single amplitudes or simulate sampling from a real quantum chip or circuit you have. And you can, for example, with Quimb and a few other packages, you can now recreate the kind of state-of-the-art classical simulation of Google's Sycamore devices. You can also simulate different objects, like just the local terms of some Hamiltonian with respect to some ansatz circuit. So here's minimizing a 10 by 10, 100 qubit depth 8 quantum circuit for the Heisenberg model, which would be well beyond most full state-based simulators. Or you could just take some ansatz quantum circuit and find the overlap between it and some state or some other unitary, and use this to, via the autodiff, compile a version of the circuits that hopefully uses far fewer gates. And you can imagine doing this to improve your real quantum circuits on a chip, or just try and explore some kind of ansatz, unitary ansatz on a quantum computer. And that's it, a brief tour.
Okay, so I think that's all of us. So I will stop sharing right now.